Welcome to the third video on solids, liquids and gases. We talked about density and measuring volumes of irregular solids in the first video, and we did an example of or two of the density calculations. And we talked about pressure in the second video and a little bit about density again. And in this one we're going to talk about fluid pressure and changes of state if we get there, hopefully. And I wanted to mention that in the last video I forgot to mention something quite important. We calculated the pressure exerted by a girl who's wearing stiletto shoes, and I talked also about an elephant, how the pressure exerted by an elephant, even though it's got a much larger mass, would still be smaller because of the difference in the areas, and therefore the pressure would be much higher here because the area is much smaller. But I forgot to mention that the total pressure that we calculated, which was 6 times 10 to the 6 pascals, or 6 million pascals, was for her whole mass on one stiletto heel. So if the question says that she's standing on two heels, we should have divided that by 2. Okay, but if she's walking and only has one leg on the floor, or she happens to be standing on one foot or whatever, then that would be accurate. But we have to take into account how many of these there are. So she's standing on her 2 feet. That spreads her pressure so that it is half also. Okay, so having said that, let's go to talk about the next idea, which is pressures in fluids. And for that we need to go somewhere around here. Okay, so pressure in fluids. First thing to define is what a fluid is. A fluid is anything that can flow, so it can either be a gas or it can be a liquid. Both of these can flow, and even sometimes you can think even of solids as being able to flow, because if you have a sand clock like that, and there are particles here and grains, and they're falling at a certain rate per second to the bottom of the clock, then there is a flow of solids there too. But anyway, mostly we think of fluids as gases and liquids, and so they exert a pressure on whatever happens to be inside of them, and also exerts a pressure on the containers that are keeping them in. So you can have a pressure exerted by a fluid such as the air on you right now when you're standing outside. If you're just standing like this, then all the air outside has a certain pressure on you. It's exerting a certain amount of pressure, and you don't feel it really, because what happens is that the pressure of the outside and the pressure of the inside of your body are the same, so they're in equilibrium, so you don't really feel it. But if you were in an unpressurized cabin in a plane, for example, where the pressure is kept at a normal amount like it is down here, and you're very high up, and suddenly the pressure was to change inside of the plane very dramatically to make it equal to what the pressure outside of the plane was, then the pressure inside of you would be so much higher than the pressure that is outside of the plane that you probably, well, some parts of you could blow up, and you could really expand and suffer from the change in pressure, because the inside of your body is in balance with a much higher pressure than the one outside of the plane. As you go up in the atmosphere, there's less and less air above you, right? So when you're up here, there's less air above you than when you're down here, so the atmospheric pressure gets less and less as you climb upwards, until it's zero when you get into outer space. Obviously there's no atmosphere there. Anyway, you could be under this could be under the ocean, and this would be fluid, and the fluid would also have a certain pressure on you, and that's why as you go deeper and deeper it gets more and more uncomfortable, and you have to start wearing a suit or have a submarine to protect you from that change in pressure. And it's quite complicated to make machines which can withstand the pressures at the bottom of the ocean, for example. That's why we've been to the moon and we've done all kinds of exciting stuff out there, but in the sense of the depth of our ocean, there's still so much that we can discover. They're trying to break records all the time, but it's quite a risky business. Right, so what's important for GCSE about pressure exerted by liquids and gases. The main thing is that the pressure, remember this part, this is very important, the pressure in fluids acts equally in all directions. So I've drawn a bunch of arrows there on this guy, and what we're saying is that if I was in water or here in the air or whatever, the pressure exerted by the fluid is the same in every direction. It's the same pressure, upwards, downwards. It doesn't. You might think intuitively that if I have a ball here in a liquid, then that the pressure of the liquid on the ball should be bigger from the top down than from the bottom up because of gravity or something like that, but it's not true. The pressure is equivalent in all the directions. Right, so hopefully you get what that means. So they could ask you to draw arrows to represent the pressure, and you have to draw them equal sizes in every direction. So if you draw 5 arrows, just draw them equally spaced and with equal length. And some questions, you're asked to calculate this thing called the pressure difference. So let's talk about pressure difference. So what is that? That is if you have for example a cylinder like this, or liquid with a liquid inside, and you ask what the difference in pressure between here and down here, where this distance is h. What is the difference in the pressure? This is all the liquid, right? But the question is about the difference in the pressure between there and there. Then there is a really handy equation that we can use, which is that the pressure difference, P, is equal to the height h times the density, which was rho, of the liquid itself, times the gravitational acceleration g. So that's 10 g, right? So if we wanted to make a triangle with this, really, we could do it like this. We'd have the P. Well, if any of these were going to move in the equation, they would come here dividing, so they would be at the bottom, right? So the P has to be at the top. P for pressure, small p, at the top, and at the bottom we'd have H and rho G. You would have rho times G, where G is 10, so this is really 10 rho. And as I said before, in the other videos, it doesn't matter if we put them the other way around, like H here and rho G here. But anyway, you can look at these in this triangle in order to solve questions. So you could find the H by dividing that by that, or you could find the pressure by multiplying these two, or you could find the density by dividing the pressure by the height, and so on and so forth. So here we're talking about the difference in pressure at one point compared with the pressure at another point. So this could be P1 and this could be P2. And so this would then be delta P, or P2 minus P1. Right? Alternatively, if they ask you between 2 points in a liquid, and like here in my diagram, the pressure here is 0 because it's at the very, very surface, then the P that you just calculated is just the pressure at the bottom, right? So if the H measures the distance from the surface down, then you can just say that the pressure at a certain depth is going to be this much, right? But if they ask you for the difference between 2 points, then you can find the pressure difference, and if you knew what the pressure was here, you could just add it onto that and you'd find the pressure down here, right? So it's going to increase as you go down, so the pressure down here is going to be bigger than up here. Right, so hopefully all of that makes sense. Now this is the reason why, if you're in a dam, if you look at the way the dams are built, as you go down in the dam, the thickness of the dam itself, of the wall, gets more thick as you go down. Why? Because the pressure down here is so much bigger, with the millions of tons of liquid that dams have. Pressure down here is so much bigger than up here, so the thickness of the dam, of the wall of the dam, actually changes as you go down, to account for that. Engineers want to save businessmen and engineers both want to save some money, so they don't want to use the same thickness all throughout, so they use how much is necessary, and down at the bottom is much more than near the top. Alright, so a question could say something like, what is the extra pressure exerted by 25 meters of water. And we'd have to use the equation which says that the pressure is equal to H rho G. And the question would have to give you the density of water, right? They would have to give you that amount. So the density of water is equal to 1000 kilograms per meter cubed. So that's an easy one to remember. 1 kilogram per liter. And there's 1000 liters in a meter cubed. You can put in 1000 liters, so that's 1000 kilograms per meter cubed. That's the density of water. And what is H? Well, H is 25 meters. That's the difference in the height between the two places, and G is just always 10. So then the pressure becomes very easy to calculate. The pressure at that depth, so the extra pressure exerted by that amount of water, would be H 25 times rho 1000 times G 10. Is it in the right units, everything? Well, let's see, that's in meters and that's in meters, so that's good. And so here we get 250, well, 25 times 10 is 250 times 1000 is 250,000. 250,000. What's the formula for the units for pressure? Well, it's pascals, which are again newtons per meter squared, same thing. So we found out a pressure at 25 meters of depth. So that's how many newtons would operate on each meter squared. And it would be operating from every direction, remember that? So why is the unit of pressure in terms of meter squared, even when you're inside of a liquid like a volume? Well, because you have a certain surface area in your body, right? Your head has a certain surface area. Every part of your body has a certain surface area, and if you put a ball in the water, well, it doesn't matter what you put in, it always has a certain surface, and the force of the liquid is always applied on that surface, right? So that's why we always write pressure as divided by meter squared, because the forces are applied on surfaces. So we can't do it per meter cubed like we do with the density of an object, kilograms per meter cubed, because that is how much mass there is inside of a volume. But here the forces act from the outside on a surface, so that's why we talk about pressure as force per meter squared in surfaces and in areas. I feel like there's something I need to qualify just to avoid confusion. Before I said that the pressure in the fluid acts equally in all directions, meaning that if I put it's not a good color, if I put something in here at a certain height or at a certain depth, then the pressure acting on from that liquid acting on here, it's going to act in every direction in the same in the same amount. So you'll get a pressure exerted from every direction, right, at that level. But that doesn't mean that the pressure all over the liquid is the same. The pressure down here, this height, is going to be higher than it is up here, right? And that's given by this equation that we were just talking about right now. So don't confuse the fact that it acts equally in all directions at any given point, which is what we were saying up here, with the fact that at different depths the pressure is going to be different. Okay, so hopefully that's clear. Okay, a way that you could check that that's true, the last thing that I was saying was if you have a can, I think I mentioned this in one of the lessons, and you had a hole here and a hole there and a hole there, and this was a container full of liquid, and you puncture these holes, you'll find that the water coming from here is going to be going further than the one coming from above. So this one would just drop like that with very little pressure, this would reach a bit further, and this would go the farthest. And that would show you the pressure in liquids increases with the depth. That would be a good demonstration to do. The idea of pressure in something like air can be understood by this idea of a can with a hole here, and maybe we plug this to some kind of machine that sucks out the air, like a vacuum machine. So this starts working and it sucks in all the air out. And what happens before that takes place, if we just have the can there in equilibrium, what we have is the can like this, and there is pressure exerted by the air inside of the can on the surface of the can outwards. and since it's in equilibrium with the outside, that is equal to the pressure of the air on the outside, right? There's millions and millions of molecules hitting each second from the outside and also from the inside, and all these forces are balanced when the can is happily in equilibrium. Now if I plug in something and I take out all the air outside, what happens to the can is this. It just crumples. As soon as I start taking the air outside, it starts crumpling. Why does it do that? Well, because all of this external pressure now doesn't have any internal pressure to balance it out. It doesn't have anything inside. I've taken away the air from inside, so this part is not there, and we only get these guys, and they crush the can. So it's not that by sucking this I am somehow crumpling it by sucking it. It's not that. The force that crumples it is all these external forces, and it crumples from every direction in the same way, and that's what we mean by fluids acting, their pressure acting in all directions. Now, a really important idea to be able to explain, well, for example, a question could ask you, explain why a fluid exerts a pressure in all directions at any point. And so in order to explain that, we need to introduce this concept called Brownian motion. And you might have heard of it in biology or chemistry or in other classes, but the idea of Brownian motion was discovered by a guy called Brown, who humbly named it after himself. And what happens is that if you look at tiny particles of matter, like smoke particles or whatever, under a microscope, so if you're looking under a microscope and here you have these particles of smoke and you can see them, then what happens is that they have this motion that is jiggling around all over the place, and we say that it's random, and you see some diagrams sometimes with, you know, like that, and the particles moving like this and then like that, and then the particle moves like that, then moves like that, and it's just continuously changing direction. So you have this kind of jiggling motion that you see under the microscope, and this led Brown to say that they must be being hit by particles, and they're jiggling around because of these impacts with invisible particles that we cannot see. So this guy was called Robert Brown, and he was the first to see this effect. He was actually looking not at smoke, but he was looking at pollen grains in a liquid. So they named this thing after him. But I think it was Einstein that then said that what was happening was that the particles of air are colliding with these guys and making them jiggle, and so this was evidence that the particles of air themselves were going at random velocities in random directions, and this led to the development of this thing called the kinetic theory of matter, which basically explains a lot of stuff using the idea of kinetic energy in matter. So as you heat it up, they have more kinetic energy, then they exert more pressure because they're going quicker, and that kind of idea we'll be talking about in the next couple of videos. All comes from this kinetic theory of matter idea. So the idea of the Brownian motion says that the particles in matter are extremely small, and that in liquids and in gases they are continuously in a state of rapid random motion. Okay, so the keywords there are the rapid random motion. Those are the particles in liquids and in gases. So the particles in liquids and gases are very small, and they are in rapid random motion. So this really is talking about fluids. And why does this help explain what I was saying before? Well, gas is just made up of those small particles that are in rapid random motion. So why would they prefer to exert the pressure in one direction than another? Why would they more of them collect here than there? Or why would they hit here less than over there? These are really small and they have a lot of kinetic energy, so they don't really care, in a gas especially, but also in a liquid, they don't really care so much about which way they're moving. At one particular depth, they're gonna be moving in all directions equally. So we can use this to explain why the pressure is exerted in all directions. So we can say that the random the random motion of gas and liquid particles, we can say it like this: the random motion of gas and liquid particles explains why pressure acts in all directions at any point. Okay, hopefully that makes sense to you. And then what happens is you increase the temperature of the materials and the pressure and the volume and the relationship between them we'll talk about in the next videos, but it's important to know that the idea of the random motion of gases and liquids particles explain very well why the pressure acts in all directions at any given point. And that comes from this experiment called, this idea called Brownian motion, which Mr. Robert Brown discovered, and then Einstein proceeded to clarify. Okay, so hopefully that makes sense. We'll do a few more questions about this law, this particular equation. I'll do another video just on this equation and some different questions that you can get on this, because I think it's an important one to learn and some people find it a little bit confusing. So we'll do some more on that. But now I'm going to move on to the next parts, and so that this series will be more of a revision one, and then we'll do a little more in depth from this equation and some other playlist. Alright, so I'll see you in the next one.